In this episode, we're going to take 3 ideas that sound abstract at first and turn them into a simple way of judging whether a decision point in a model is doing useful work. When beginners first hear entropy, information gain, and Gini, it can feel like someone swapped real learning for mysterious vocabulary, but these concepts are actually about a very familiar question. Did this split make the data more organized or more messy? In many classification models, especially tree-based thinking, you repeatedly split data into smaller groups using questions like, is this value above a threshold, or does this category match a condition? Some splits create cleaner groups where most items share the same label, and other splits create mixed groups where you still have a lot of uncertainty. The exam often tests whether you understand what makes a split good at a high level, not whether you can compute every number perfectly. Our goal is to help you reason about split quality in plain language, recognize what these measures are trying to optimize, and avoid common misunderstandings that make the topic feel harder than it is. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at Cyber.Author.me in the Bare Metal Study Guide series. A split is a choice that divides your dataset into parts, and the quality of that choice depends on what you want those parts to look like afterward. If you are trying to classify items, a useful split creates groups that are more predictable than the original mixed group, meaning that within each new group you are more confident about the label. That confidence is the heart of the topic, because entropy and Gini are both ways of measuring uncertainty or impurity in a group. If a group is perfectly pure, meaning every item has the same label, there is no uncertainty, and the impurity measure should be low. If a group is evenly mixed between labels, there is high uncertainty, and the impurity measure should be high. Information gain then becomes a way to compare before and after, asking how much uncertainty you removed by making the split. Beginners sometimes assume split quality is about making the dataset smaller, but smaller is not the goal by itself. The goal is to create smaller groups that are easier to predict correctly, because that is what makes a tree-like model useful rather than just complicated. Entropy is one of the most common ways to quantify uncertainty, and even though it has a mathematical definition, the intuitive meaning is surprisingly straightforward. Entropy is high when outcomes are unpredictable and low when outcomes are predictable. And for classification, that means it reacts to how mixed the labels are. If you have a group where almost everything is one class, entropy is low because you can guess the label correctly most of the time without much hesitation. If you have a group that is half one class and half another, entropy is high because you are genuinely uncertain what label a random item from that group will have. The important beginner takeaway is that entropy is not measuring how many items you have, but how surprising the label is when you pick an item at random from that group. That surprise idea matters because a split that reduces surprise is a split that makes the classification task easier in the downstream branches. When an exam question asks about entropy at a split, it is usually asking whether you understand this uncertainty logic, not whether you remember the exact formula. Information gain builds directly on entropy by turning the uncertainty measure into a comparison tool. Before the split, you have one group with some entropy, and after the split, you have multiple groups, each with its own entropy. Information gain is essentially the amount of entropy you removed, which means it measures how much more certain you became by making that split. A key detail is that you do not just average the entropies of the child groups equally, because a split that creates one tiny group and one huge group should not be judged the same as a split that creates two balanced groups. Instead, you weight the child entropies by how many items fall into each child group, because the large group represents most of your data. This weighting is why a split that makes a very pure tiny group but leaves the majority group mixed might not be as valuable as it looks at first glance. Beginners sometimes assume that any creation of a pure leaf is automatically good, but information gain forces you to account for how much of the dataset benefited from the purity improvement. On the exam, if you see two competing splits, the one that reduces overall uncertainty more broadly is often the one with higher information gain. To make this concrete in your mind, imagine you start with a group of items that includes both labels, and your goal is to separate them. If you split on a feature that cleanly separates most of one label into one side and most of the other label into the other side, you will end up with child groups that are each less mixed than the parent. That means each child group has lower entropy than the parent, and the weighted average of child entropies will be lower than the parent entropy, producing positive information gain. If you split on a feature that does not actually relate to the label, you might create child groups that are just as mixed as the parent, which means entropy does not drop much, and information gain will be small. This is why these measures are useful. They help the model choose splits that are likely to improve predictability rather than splits that merely reorganize the data without making labels clearer. Beginners sometimes interpret information gain as a magical property of a feature, but it is always relative to a specific split in a specific dataset. If the dataset changes, the gain can change because the label mix and feature relationships change. Gini impurity is another way to measure how mixed a group is, and it is often used as an alternative to entropy because it is simpler to compute and behaves similarly in many situations. The intuition is still the same. Gini impurity is low when a group is mostly one class and high when a group is more evenly mixed. One way to think about it is as a measure of how often you would be wrong if you randomly guessed a label according to the class proportions in the group. If the group is 90% one class and 10% the other, a proportion-based guess would be correct most of the time, so impurity is low. If the group is 50-50, proportion-based guessing would be wrong quite often, so impurity is high. The exact numeric values differ from entropy, but the qualitative meaning is aligned. For exam questions, you do not need to treat Gini as a completely different universe. Treat it as another uncertainty meter that rewards purity. The main advantage of understanding both is that you can recognize that models may choose splits by maximizing impurity reduction, whether that impurity is measured by entropy or by Gini. Once you understand impurity measures, split quality becomes a predictable idea rather than a memorization task. A good split reduces impurity, meaning it produces child groups that are closer to pure than the parent group, and the best splits reduce impurity in a way that affects a large portion of the data rather than only a small corner. This is why weighted impurity matters and why balanced splits can be valuable. A split that creates two moderately pure groups can be better than a split that creates one perfectly pure but tiny group and leaves a large group still mixed. Beginners sometimes think the model should always chase perfect purity immediately, but tree growth is a sequence of choices, and early splits need to create structure that can be refined later. The model wants to make the label distribution easier to predict step by step. If early splits isolate the clearest signal that affects many cases, later splits can handle edge cases and smaller patterns. When you reason about split quality, you are really reasoning about how well the split prepares the next steps to finish the classification job. A very common beginner misunderstanding is assuming that a split is good if it produces many branches or many distinct groups. But more branches do not automatically mean more information. If you split in a way that fragments the data into many small groups without improving label purity, you may actually make the model worse because you reduce the reliability of each group's statistics. This is where you start to see the connection between split criteria and overfitting, even if you are not doing implementation. A tree can always split until every group is pure if you allow it to keep splitting on increasingly specific conditions, but that does not mean the model learned a generalizable pattern. It might simply be memorizing quirks of the training data. Impurity measures help guide splits toward useful reductions in uncertainty, but they do not, by themselves, guarantee generalization. Exam questions sometimes hint at this by describing a tree that becomes very deep or splits on very specific values, then asking what risk that creates. A mature answer recognizes that purity on training data can come from memorization rather than real signal, and split quality must be considered alongside the broader goal of generalization. Another subtle point is that information gain can be biased towards splits that create many distinct outcomes, especially when a feature has many possible values. If a feature has a large number of unique categories, it can create child nodes that are very small and sometimes pure simply because each category appears only a few times. That can produce a large reduction in impurity on the training set, even if the split is not truly meaningful. This is a classic issue in decision tree learning and one reason you need to be cautious when interpreting very high gain from a highly granular feature. As a beginner, you do not need to memorize all the fixes, but you do need to understand the failure mode. A split can look great because it slices the data into tiny pieces, not because it discovered a stable pattern. On an exam, if you see a scenario where a feature like an identifier or a high cardinality category is used to split, and the split looks perfect, you should be suspicious. Identifiers often encode uniqueness rather than meaningful predictive structure. Recognizing this helps you choose answers that emphasize generalizable signal rather than accidental memorization. It is also useful to connect entropy and Gini to the broader idea of uncertainty you already learned in probability topics, because the mental model is consistent. When a node has a mixed label distribution, you are uncertain about the label of a random item from that node, and that uncertainty can be measured. A split that creates nodes with more skewed distributions reduces that uncertainty, which means the model gained information about what label to expect given the split condition. This is why the phrase information gain is so literal. The split gives you information that reduces your uncertainty. Thinking of it this way helps you avoid treating the measures as arbitrary math. The measures exist because we want a systematic way to choose splits that make the label more predictable. In practical data AI terms, you can think of each split as a question that partitions the space into regions where the outcome is more consistent. The better the question, the more consistent each region becomes. Exam questions that ask which split is better are really asking which question produces regions with clearer outcomes. You should also be careful not to confuse purity with fairness or with correctness in every subgroup, because a pure node can still represent an unfair or biased partition if the data itself reflects bias. A split might separate data along a variable that correlates with the label due to historical bias rather than a causal or acceptable relationship. Impurity measures would treat that split as excellent because it improves prediction, but prediction quality alone does not guarantee the split is appropriate in a real-world decision system. For this certification context, you are usually being tested on the statistical and modeling logic, but it is still valuable to remember that impurity measures are purely about label predictability. They do not ask whether the split aligns with ethical constraints or with policy requirements. In many systems, you must consider additional constraints beyond pure predictive performance. If an exam scenario hints at sensitive attributes or unintended discrimination, a correct answer may involve caution about which features are used for splitting, even if they produce strong purity. This is part of becoming a mature model evaluator rather than a metric worshiper. Another practical skill is being able to reason about split quality without doing full calculations, because many exam questions are designed to be solvable by inspection. If you see a parent node that is evenly mixed and one candidate split produces child nodes that are both still evenly mixed, you can conclude the split did not help much, so information gain or impurity reduction would be small. If another candidate split produces a child node that is almost all one class and another that is almost all the other class, you can conclude impurity dropped significantly, so the split is likely better by either entropy-based gain or Gini reduction. You do not need exact numbers to see the direction. The key is to focus on how mixed each child node is and how large each child node is. A perfect but tiny node is less valuable than a strong improvement across most of the data. This qualitative reasoning is often enough to select the correct answer quickly. If you find yourself tempted to do heavy math under time pressure, it is usually a sign that you missed a simpler purity comparison that the question was designed around. It also helps to understand how these split criteria relate to the idea of greedy learning, because decision trees often choose the best split at the current step without guaranteeing it is part of the best overall tree. The model evaluates many candidate splits and picks the one that reduces impurity the most right now. That greedy choice often works well in practice, but it can also lead to local choices that look good early while not producing the best long-term structure. For exam purposes, the important takeaway is that entropy, information gain, and Gini are used as local decision rules that guide the tree-building process. They do not represent a guarantee that the final model is optimal in every sense. This is another reason overfitting can occur. The model can keep finding small impurity reductions that fit training quirks. Understanding the greedy nature of splitting helps you interpret why pruning, depth limits, or other controls are often used to prevent the tree from becoming overly complex, even when each split looks justified by a small gain. You do not need to configure those controls, but you should understand the motivation behind them. Because these measures are often discussed together, it is useful to compare entropy-based information gain and Gini-based impurity reduction in a way that reduces confusion. Both are trying to do the same job: quantify how mixed labels are in a node and reward splits that create purer children. In many practical datasets, the two measures choose similar splits, especially when differences between candidate splits are large. Where they may differ is in how they scale and how they respond to certain distributions. But for a beginner exam context, the key is that both measure impurity and both support the same intuition. If a question asks which split improves purity, you can often answer without caring which impurity measure is used, because the direction of improvement is obvious. If a question specifically names entropy and information gain, focus on the idea of uncertainty reduction. If it names Gini, focus on impurity reduction and proportion-based guessing error. Either way, you are still describing how the split makes labels more predictable. This reduces the mental burden because you are not learning two unrelated systems, but two versions of the same concept. Finally, bring the whole idea back to the student-friendly question that should always guide your reasoning. After the split, do I know more about what label to expect? If the answer is yes, impurity went down and the split is good. If the answer is no, impurity stayed high and the split is not helpful. Entropy gives you a formal way to quantify that uncertainty, information gain gives you a way to measure the improvement, and Gini gives you an alternative impurity measure that behaves similarly. Along the way, you also learned why weighting by group size matters, why high cardinality features can create misleadingly strong splits, and why purity on training data does not automatically mean generalizable performance. You learn to reason qualitatively about child node label mixes so you can choose the better split quickly under exam time pressure. Most importantly, you built a mental model that makes these terms feel like tools for clarity rather than obstacles. When you can explain split quality as uncertainty reduction, you are using the same reasoning patterns that support later topics like feature importance, overfitting diagnosis, and evaluation under changing thresholds. That consistency is what turns a collection of definitions into real understanding.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.